Welcome to Unit 1, Limits and Continuity, Calculus AB. Part 1, How to Evaluate Limits. Firstly, let's define what a limit is. A limit is the value that a function approaches as the input x gets closer to a specific number. It tells us how a function behaves near a point, even if it's not defined exactly at that point. There are three main ways to evaluate limits. We can use graphs, tables, and algebra. Start with a simple example. The limit as x approaches 2 of the function f of x equals x squared plus 2. Graphically, use a graphing utility to observe the behavior of the function as x approaches 2 from both sides. Numerically, make a table of values that approach 2 from the left and right. If the y values get closer to a single number, that number is the limit. Algebraically, plug in the value. If you get a normal number, that's the limit. This is an example of a function where you will need to do more work. If you get 0 over 0, this is an indeterminate form, and it indicates that you need to do more. Part 2. When does a limit exist? A limit exists when the y values from both the left and right sides of a point exist and are equal. If the left and right limits are equal, the limit exists. If they're different, the limit does not exist. If either side doesn't exist, the limit does not exist. Graphical examples help make this concept clearer. Part 3. What to do with 0 over 0, indeterminate forms. When plugging in a value that gives 0 over 0, use strategies like factoring or rationalizing. Example 1. X squared minus 9 over x minus 3. Factor the numerator and cancel terms to evaluate the limit. Example 2. Square root x minus 2 over x minus 4. Multiply by the conjugate to simplify and find the limit. If you know how to derive the functions in the numerator and denominator, you can use L'Hopital's rule. But in this video, we will focus on some basic methods that do not require derivatives. Part 4. Special trig limits. It is a good idea to memorize these special trig limits as they are essential in many calculus problems. Basic limit. Limit as x approaches 0 of sine x over x equals 1. Reciprocal. Limit as x approaches 0 of x over sine x equals 1. Cosine limit. Limit as x approaches 0 of 1 minus cosine x over x squared equals 1/2. Sign difference. Limit as x approaches 0 of sine kx over x equals k. Cyclic limits. Limit as x approaches 0 of sine x minus x over x cubed equals 0. Part 5. Discontinuities and Transformations. Functions like absolute value x minus c over x minus c, or x minus c over absolute value of x minus c, show sharp discontinuities at x equals c. It is important to understand how transformations affect discontinuities. Shifts move discontinuities, but don't remove them. Reflections flip the behavior of discontinuities. Scaling changes the size of discontinuities, but not the location. Factoring or simplifying can sometimes remove discontinuities. Consider the function x minus 2 over x squared minus 4. When plugging in 2, the function evaluates to 0 over 0. This indicates a discontinuity. However, if you factor the term in the denominator, the common factor x minus 2 cancels out. When plugging in 2, the function now evaluates to 1/4. Part 6. Types of discontinuities. There are 3 types of discontinuities: removable holes, jumps, and asymptotes. With removable holes, the limits from the left and right exist and are equal, but the function is not continuous because the function is not defined at that point. With jumps, the limits from the left and right exist, but are not equal. The function value is defined, however, at all points. With asymptotes, the limits from the left and right do not exist, and the function value is not defined. Part 7. Conditions for continuity. There are 3 conditions for continuity. A function is continuous at a point if 1. The function value exists. 2. The limit exists and is the same from both sides. And 3. The function value equals the limit. All 3 must be true for a function to be continuous. This means that functions with holes, jumps and asymptotes are considered to be discontinuous. Part 8. Limits at infinity and horizontal asymptotes. When evaluating limits at infinity for rational functions, remember these helpful rules. If the degree of the numerator is greater than the degree of the denominator, the limit is positive or negative infinity. If the degree of the denominator is greater than the numerator, the limit is 0. If the degrees of the numerator and denominator are equal, divide the leading coefficients to get the limit. Part 9. Squeeze theorem. Squeeze theorem, or sandwich theorem, is a calculus tool used to determine the limit of a function by squeezing it between 2 other functions whose limits are known. Squeeze theorem states that if a function g of x is between 2 functions, h of x and f of x for all numbers, and at some point x equals k, we have f of k equal to h of k, then g of k must also be equal to them. This is an important theorem to know, so make sure you remember it. Part 10. Intermediate value theorem IVT. If a function f of x is continuous on a closed interval from a to b, and there's a value m between f of a and f of b, then there must be some value c, where the function's value equals m. Some common misconceptions about intermediate value theorem. Intermediate value theorem does not tell you what the value of c is, only that it exists. It doesn't work if the function is not continuous. M must be between f of a and f of b, not outside that range. These foundational ideas, how limits work, when they exist, and how continuity connects to them, are essential to understanding calculus. Review these concepts and practice applying them to graphs, tables and equations to build your confidence and be successful in your math class. Thank you for watching. Please subscribe for more videos.